Hello everyone, and welcome back to another GIS lecture video. And in this lecture video, I want to continue our discussion talking about georeferencing by moving on to the third step in the georeferencing process. So up to this point, we found points of interest in both the unreferenced dataset and the referenced dataset, and we called those tie points or control points. And then we used those control points to parameterize a transformation. And rather than focusing on the math behind it, we talked, generally speaking, about four different sort of transformation primals, if you will, that are the sorts of things conceptually that we can do to make the unreferenced data match the referenced data. We had translation, where we changed the position. We had rotation, where we changed the orientation. We had scaling, where we changed the size. And then we had skewing, or skew, where we changed the angles between lines. And the key point I made at the end of this was that something that we were not doing under this type of transformation was bending or warping lines, right? Under all scenarios, all straight lines were kept straight, right? We did not bend or alter the shape of the line, right? We changed the size and we changed the angles, but we never bent any straight lines, okay? So the third step that we're going to talk about today is a little bit of a letdown, right? Because up to this point, maybe you assumed, because I haven't said otherwise, that we could do this with 100% perfect accuracy, right? That we could take this unreferenced data set and make it match perfectly to a referenced one. Well, unfortunately, that's usually not the case, right? That's usually not the case. And so the third and final step of the georeferencing process is actually to assess the accuracy, right? So step 3 in this process is to assess accuracy. Right, to assess the accuracy of what we've done. And what I want to do is I want to take that example that we've talked about with this idea of having that CAD image, overlaying it on a referenced ortho image. And what I've done here is I've actually done the georeferencing in a georeferencing software, and I've screen captured the ending of it with the CAD image as mildly transparent and the actual ortho image underneath being non-transparent, so you can see both at the same time. And hopefully visually you can see that we have the CAD image not perfectly lining up, right? For here, for example, right, this line right here is the arch or arc for the entrance. But on the ortho image, right, we can see that the ortho image has that same arc being right here. Has that same arc being right there. So this discrepancy right here, this is an error in georeferencing, right? So this yellow area right here, I'm about to draw in, right? This here, right? This is an error, right? This is an error. Same thing down here, right? The CAD file makes its circle go like this, whereas the ortho image has the circle going like this, okay? That would also be an error. And so what I've done is I've actually taken this set of tie point, this tie point right down here, right? And I've magnified it to here so that we can look at what these tie points look like when we zoom in, right? So this green right here, this is where the point was supposed to be, right? So this is where the point was supposed to be. Right, because this whole thing right here, this is a control point, right? We have this control point right here. This was where the control point was supposed to be after the transformation. Right, this red up here, this is where the point actually ended up. Right, this is where the point actually ended up after the transformation. Okay? And so this distance, right, this distance is error. Right? At the most fundamental level, right, the difference between where the control point was supposed to end up and where the control point actually ended up in the unreferenced data after we applied the transformation, right, that difference, which is a distance, is the error. Okay? So hopefully that makes sense. I just want to take a step back and sort of go through this again a little slower. Right? We can see by this example that no matter what we do, right, our georeferencing will never be perfect. And we'll talk more in the next video about how we can improve the accuracy. But for this quick example, right, we can see that I've done a particularly bad job here. But we can see that, this is never going to be perfect. That we're always going to have deviations from where it should be relative to where it actually ended up after the transformation. And what we can do to assess the accuracy is we can actually look at individual points. And we can see where the point was supposed to be relative to where the point actually ended up. And we can calculate that distance. And that distance is a numeric representation of the error in the transformation, okay? So when we're talking about error, what we're talking about is the distance between where a point should be and where it ended up, right? So broadly speaking, when I say error, right, it's the distance between where a point should be and where it ended up. Right? Okay, so with this concept of error in our minds, I want to talk about the way that we actually quantify the error. Right? How do we assess the accuracy? And the way we do that is with something called root mean square error. Root mean square error, or sometimes you'll see it referred to as RMSE. Root mean square error. Right. I'm going to give ourselves just a little bit of space here. And I want to write down the equation for RMSE. I don't necessarily expect you to be able to calculate this by hand. We'll go through an example of how to calculate it in Excel later. But I do want you to understand the equation so you can see where all the different pieces are coming from. Right? So RMSE, right, is defined as, well, we can define it based on just breaking the name apart, right? Root means we're taking the square root of something, right? Okay, root, square root. Mean means we're taking the mean of something, which means we're going to be dividing something by the number of that something, right? That's what it means to take the mean. Square means we're going to be squaring something. Right? What are we going to square? We're going to square the error. Well, what is the error? The error is just the distance, right? The distance between where the point should be and where the point ended up, right? And we call this distance, d, okay? So let's go ahead and break apart the two pieces in here that aren't mathematical symbols, right? Because most of this is just mathematical symbols, okay? Right? RMSE, the big thing we have on the bottom here, this bottom piece, this n, this is the number of points used to assess the accuracy. Right, and so if we were to look at our specific example, sliding away from the equation for just a second, right, if we were to use our specific example here and we were to assess the accuracy here, right, our specific example would have 4 points, right? Because again, you have to realize the green and the red, that is 1 point because it's the location where it should be, and the red is the location where it ended up, but it's still the same point, right? Because these are those control points, right? So in this case, in our specific example here, n would be 4. 1, 2, 3, 4. Right? So specific example. Our specific example is 4. Right. So what's this distance up here? This distance, or this d, we'll just reiterate that this d is distance. Well, it's the distance of what, right? What's the distance between where the point should be and where the point ended up? Okay. The distance that we're going to use is called Euclidean distance. So specifically, we're talking about something called Euclidean distance. And so in the next video, I'm going to briefly describe, in case you don't know how to calculate Euclidean distance, I'm going to calculate that. I'm going to show an example of how to calculate that and explain what that is. But for right now, what I want to end this video on is understanding conceptually that this root mean square error is basically just a measure of the average distance between where the point should be and where the point ends up, right? So to sort of quantify that, right? RMSE generally, this is a broad interpretation, right? A broad interpretation of RMSE. Is the average distance is related to, because again, it's not a perfect mathematical calculation, but it's basically a measure of the average distance of points from where they should be. Right. So a broad interpretation is it is basically just the average distance of points away from where they should be. And that would make sense, right? Because so we remove the square, we remove the square root, we're taking an average of distance, this distance being from where a point is from where it should be. Okay? So how do we actually interpret this idea? generally speaking, lower is better, right? I'm gonna end this video by making something lower is better. Lower is better. And that's what I want to leave this video off. That when we try to assess the accuracy, we do so with this idea of RMSE, and the result is basically an average distance of points from where they should be. And the way that we interpret it is that lower is better. So in the next video, I'm going to go over Euclidean distance. So if you feel comfortable with that, feel free to skip it. Otherwise, it's going to be just a short video. The video after that, I want to talk about how we can improve this accuracy and what are some things that might be causing it to be poor. Okay, so with that, as always, if you have any questions, please reach out. Thank you.